Hey everyone, welcome back. Today we're doing a deep dive on super resolution satellite imagery. Yeah, it's about using AI to take those blurry satellite pictures and make them, well, super sharp and detailed. Our source material actually starts with a story from the World Bank. They were working with governments who really needed those super high resolution satellite images, for tracking projects, managing resources, even spotting illegal buildings. But those crystal clear images, they come with a hefty price tag, $7 per square kilometer. So naturally that got people thinking, there's gonna be a more budget-friendly way to get that same level of detail. Enter super resolution. But can AI really take those low resolution satellite pics and make them as good as the expensive ones? And I don't know about you, but I'm kind of curious how this even works. Like, how do you teach a computer to add details that aren't even there in the first place?
It's interesting. It's kind of like how our own brains work. When we see a blurry picture, our minds try to fill in the blanks, right? We use what we already know to guess the missing details. Super resolution AI, it does something similar. But instead of guesswork, it's trained on tons and tons of data, images, to learn the patterns. So it learns the relationships between those low-res and high-res details, if that makes sense.
So the AI is basically learning to see, like we do, but way, way faster, and with like a million times more reference points. Our source actually gave a cool example. They used this tool called Magnific to upscale a blurry photo of Palm Island. And the results were, visually stunning. The image went from blurry to incredibly detailed, but, and this is a big but, the AI, got a little creative. It started adding things that weren't actually there, like trees in the ocean, and a roof on a building that, didn't actually have one in real life, even phantom cars. And while that might be fine for, an art project, it's a huge problem when you're talking about using these images for, actual analysis. Accuracy is key, right? We need to know that what we're seeing is actually real. So how do we make sure the AI is giving us accurate results, not just visually impressive ones? What's the difference between a cool tech demo and a tool scientists can actually rely on?
Yeah, you really got to make sure it's accurate, especially if you're using these images for, scientific analysis or making big decisions. It's like, think of baking a cake, right?
Mm-hmm.
You need the right ingredients and the right recipe to end up with something delicious.
And in the world of super resolution, what are those key ingredients?
Well, just like cake needs good flour and sugar, super resolution AI needs high quality training data. And by that, I mean having pairs of low resolution and high resolution images, of the same area taken at the same time.
So those image pairs are basically like the recipe book for the AI. It uses them to learn how to go from blurry to sharp.
Exactly. It helps the AI understand what details are usually lost when you go from that high resolution down to low resolution.
That makes sense. But I imagine actually finding enough of those perfectly matched image pairs is easier said than done.
Oh, absolutely. It's a huge challenge. Think about it. Even something like cloud cover can mess things up.
Ah, right. One well-placed cloud could throw off the whole training process?
Exactly. And then there's the fact that you need access to those high-resolution images in the first place, which, as we've said, can be super expensive.
So finding the right data, that's challenge number one. What about the recipe itself? Our source mentioned different types of AI models for super resolution. What's the deal with those?
Yeah, so just like you have different cake recipes, you also have different AI models for super resolution. And each one has its own strengths and weaknesses, its own quirks.
Okay, so walk us through it. What are our options on the super resolution menu?
Well, there's this one approach called pan sharpening. Think of it like a classic no-fail cake recipe. It's been around for a while and it's pretty reliable. Basically, pan sharpening takes a high-resolution black and white image and combines it with a lower-resolution color image of the same area. By kind of merging the two, you get a final image that's sharper than that original color image you started with.
So it's like taking the sharpness of a black and white photo and then layering the color information on top.
Yeah, exactly. It's clever, but it's limited in how much it can actually improve the resolution.
Right, because it's not actually using those more advanced AI techniques.
Exactly. It's great for enhancing certain details, but it's not going to magically reveal stuff that wasn't there in the first place.
So what about those fancier AI models? What else is out there?
Well, that's where things get even cooler. We have neural networks. They're super versatile and powerful.
So these neural networks, they're like the multi-tiered, super complex cakes of the AI world.
I like that analogy.
Yeah.
Yeah, they're designed to mimic the way our brains work with all those connections.
So they can learn really complicated relationships between those low-res and high-res images.
Yeah, and they can do it with remarkable accuracy. It's pretty amazing.
Yeah.
But there is a bit of a catch. They need a ton of data to learn effectively.
Right, like we were talking about before, those image pairs.
Exactly. Neural networks need to see a ton of examples to really get it.
And I'm assuming if that data is bad or if there just isn't enough of it, the results aren't going to be great.
Exactly. It's like trying to bake a cake with only half the ingredients. And even if you have all the right ingredients, you still need to bake that cake properly. And that brings us to model calibration.
Model calibration. Is that where we like fine-tune the AI, make sure it's not putting any surprise palm trees in our ocean?
That's a good way to put it. It's about
Cool.
making sure that those results are as accurate and reliable as possible.
So how do you tune an AI?
It often comes down to two main things: the loss function and the hyperparameters. So the loss function, that's basically a way of measuring how close the AI's output is to the actual real thing.
So the lower the loss, the better the AI is doing.
Exactly. And that's where hyperparameters come in. Think of those like the knobs and dials we can adjust to fine-tune how the AI learns.
So if the loss function tells us how well the AI is doing, the hyperparameters are our tools to make the AI even better.
Exactly. It's about finding those perfect settings for the AI to,
Awesome.
learn most effectively from all that data we were talking about.
So even with this super complex AI, there's still a human element involved. We're still the ones like guiding the process.
Absolutely. And speaking of results, we need to talk about how we actually measure the accuracy of these images, once they've been enhanced.
Right, because we can't just rely on the wow factor. A cool looking image isn't necessarily an accurate one.
Yeah, it's tempting to just trust those before and after pics, but looks can be deceiving.
It's like they say, can't judge a book by its cover, right?
Exactly. Our source, actually, they point out that some research gets caught up in those eye-catching visuals, but they don't always back it up with, solid evidence that the results are actually accurate.
So we need ways to measure how well these algorithms are actually performing. But how do you do that with something like this? It's not like we can just hold a ruler up to the image and see which one's closer to the original.
That's where metrics come into play.
Metrics.
Yeah, think of them like the judging criteria in a baking contest, right?
Right.
You wouldn't just pick the prettiest cake, would you?
I mean, I might.
Well, sure, but you'd also want to know how it tastes. How well baked is it? Did they actually follow the recipe? Metrics, they give us ways to evaluate super resolution, in a measurable way.
Okay, so what are these super resolution judging criteria? What are we looking at?
One of the most popular ones is called PSNR, stands for peak signal to noise ratio.
Catchy.
Right. Basically, it compares the pixel values in the super result image to the original high resolution image.
So the higher the PSNR score, the more the super resolved image matches the original.
Exactly.
But I'm guessing no single metric tells the whole story.
You got it. PSNR, it's a decent starting point, but it doesn't capture everything. It's like judging a cake just on how smooth the frosting is,
Yeah.
You're missing out on all those other important details like the texture, the flavor.
So we need metrics that go beyond just the surface level, something that really gets at the nuance of a good super resolution.
Right, that's where SN comes in. Yeah, it stands for Structural Similarity Index. It's a bit more, I guess you could say, sophisticated than PSNR. It considers things like luminance, contrast, and the overall structure of the image.
So it's like judging a cake on its flavor and texture, not just how pretty it looks.
Exactly. It gives us a more, I guess you could say, holistic view.
Okay, that makes sense. But even with these fancier metrics, are we really getting the full picture? What if an AI is really good at mimicking certain details, but totally misses the mark on others?
That's a great point, and it's why it's smart to use a bunch of different metrics together. Like, there's another important one called RMSE, root mean squared error. And it basically quantifies the differences between those two images, the super resolved one and the original. So the lower the score, the better.
So it's like we're giving the AI a report card, right?
Right.
And each metric is like a different subject.
Yeah, I like that analogy, and it highlights why you don't want to just rely on one single metric to judge how well an algorithm is doing.
This is fascinating stuff, but after diving into all this, I gotta ask, is super resolution all it's cracked up to be? I mean, are we about to live in a world where we don't need those expensive high-res images anymore?
Well, that's the million-dollar question, isn't it? And while super resolution is super promising, it's important to remember it's not perfect.
So even the smartest AI can't work miracles.
Pretty much. There are still some fundamental challenges. Like, at the end of the day, you're trying to create information where there wasn't any to begin with. Our source had a good example about Imagine trying to count individual roof tiles in a satellite image.
Yeah, you need some serious zoom for that.
Right. Sometimes you just need that ultra-high resolution to see those really fine details.
It's like those incredibly detailed miniature cakes I've seen online. Like at some point you hit the limits of what you can physically create, even if you're super skilled.
Exactly. It's not just about those really tiny details. It's also about the complexity of what you're looking at. Like trying to analyze a dense forest, for example, or track small objects that are moving around. Those are tricky situations, even for those really advanced algorithms.
So it sounds like super resolution is a really powerful tool with a lot of potential to change how we use satellite images. But it's not a magic solution to every problem.
Exactly. It's about understanding both the strengths and the limitations.
Yep.
Like it's a fantastic way to get more out of the data we already have. But it's not going to replace actually going out and getting those super high resolution images when you absolutely need them.
Right. It's about using the right tool for the job.
Absolutely.
Well, this has been an awesome deep dive into the world of super resolution satellite imagery. We've covered how AI is being used to make blurry images sharp, learned about the different types of AI models, and even gotten into the nitty-gritty of how we measure success. And of course, we've also talked about the importance of understanding the limitations of this technology, because as with anything powerful, it's up to us to use it responsibly. But for now, we're going to wrap up this deep dive. We hope you've enjoyed the journey as much as we have. Until next time.